In linear algebra, we often focus on how a single vector transforms, but many applications require us to measure how two distinct vectors interact. This is the role of a bilinear form. It is a function that takes two vector inputs, alpha and beta, and processes them to output a single scalar value. For a function to be bilinear, it must follow specific rules of linearity. For instance, it must be linear in its first argument, as shown here. This means if we keep the second vector, beta, constant, the function behaves exactly like a standard linear transformation on alpha. The same requirement applies to the second argument if the first is held constant. You can create a simple version of this by taking two separate linear functionals and multiplying their outputs. That product satisfies the requirements for both arguments. Enforcing this two-way linearity allows us to systematically quantify the relationship between pairs of vectors, providing the foundation for more complex geometric measurements. Consider two vectors, alpha and beta, expressed as components within a two-dimensional basis. When we plug these into our bilinear form, the linearity rules allow us to expand the expression and pull the scalar coordinates, the x and y values, directly to the front. We are left with a sum of those scalars multiplied by the function's output for each basis pair. Because the basis vectors are fixed, these outputs are just constants. We can organize every possible combination of these values into a square matrix, A. This organization allows us to rewrite the entire operation as a sequence of matrix multiplication, x transpose times A times y. This direct correspondence means that every bilinear form on a finite dimensional space is represented by a unique matrix, and conversely, every square matrix defines a specific bilinear form. While matrices represent both linear operators and bilinear forms, they transform differently when we change the basis of the underlying vector space. A linear operator uses the inverse of the change of basis matrix, P. A bilinear form, however, requires the transpose of P. This requirement stems from the x transpose in our multiplication sequence. When we change the coordinates for that first vector, the basis matrix is transposed along with it. Let's look at how this works. Here is a bilinear form, its matrix representation A, and a new basis set. Pause the video and determine the new matrix representation using the transpose formula. Calculating P transpose times A times P reveals a much simpler result, a diagonal matrix with entries 0 and 4. Using the transpose formula in this way allows us to simplify the representation of geometric interactions, making them easier to calculate. From the perspective of a single vector, if we lock in alpha and leave the second slot empty, we create a linear functional. The rank of a bilinear form equals the rank of its matrix. If it has full rank, the form is non-degenerate. In a non-degenerate form, no non-zero vector is invisible to the rest of the space. For any vector you choose, there is always another vector that yields a non-zero interaction. The most common example of this is the standard dot product. It is a non-degenerate bilinear form where the representing matrix is simply the identity matrix. Mastering these forms provides the tools needed to analyze quadratic equations and advanced geometry. For the full derivations of these theorems, refer to Chapter 10 of Hoffman and Kunze.